Hi everyone, welcome back. In today's video, we are kind of going to be using the same idea from part B, except this time we're working with a reaction. So here we have ethanol reacting on a catalytic surface to produce acetaldehyde and hydrogen at 548 Kelvin and 101.3 kilopascals. So here you can see I've already labeled our catalytic surface and our bulk surface. I'm going to go ahead and label ethanol as 1, acetaldehyde as 2, and hydrogen as 3. And these are all in the gas phase. So for this example, we are going to have our ethanol, which is flowing down from our bulk surface to our catalytic surface. We're then going to have our acetaldehyde flowing from the catalytic surface to the bulk surface. Likewise, we're going to have our hydrogen flowing from the catalytic surface to our bulk surface. We're also given a handful of other information, so let's write that down quickly. We have our pressure set at 101.3 kilopascals. We have our temperature set at 548 Kelvin. And then we are given our diffusion coefficient. So the diffusion coefficient of ethanol through acetaldehyde is 72 millimeters squared per second. The diffusion coefficient of ethanol through hydrogen is going to be 230 millimeters squared per second. And our diffusion coefficient of the acetaldehyde through the hydrogen is going to be, again, 230 millimeters squared per second. And I'm going to turn these into our SI units just to make this a little bit easier when we go into Excel and we actually begin to solve things. So this is going to be 72 times 10 to the negative 6 meters squared per second. Likewise, this is going to be 230 times 10 to the negative 6 meters squared per second, and then 230 times 10 to the negative 6 meters squared per second again. We are also given this distance from our bulk surface to our catalytic surface. So it's going to be this distance right here is given to us. And that is going to be delta is equal to 1 millimeter. And again, I'm going to change those to be an SI unit. So this is going to be 1 times 10 to the negative third meters. We are given our mole fractions at the bulk surface. So I'm going to write those in up here. We have the mole fraction of ethanol at our bulk surface is going to be 0.6. The mole fraction of our acetaldehyde at our bulk surface is going to be 0.2. Likewise, the mole fraction of our hydrogen at this bulk surface is going to be 0.2. We're also given a rate constant for our reaction. So this reaction rate is going to be K sub R, and this is going to be equal to 10 mole per meter squared second mole fraction. It's going to be 10 mole per meter squared second mole fraction. And like I said, we can use our Stefan Maxwell equation to solve for this because we want to find our boundary conditions and the surface mole fraction of ethanol and the reaction rate per area. So we're going to have to use our Stefan Maxwell equation. This is one we're pretty familiar with at this point, so I'm just going to write this out. This is going to be the driving force of species I, which is equal to the derivative of the mole fraction of species I with respect to our position, which in this case, we're going to have it in the z direction. And that is equal to the summation of the mole fraction of species I multiplied by the molar flux of species J minus the mole fraction of species J times the molar flux of species I. This is divided by our overall concentration and the diffusion coefficient of species I through J. So if we want to start talking about our first component, which is our ethanol, we can write this out as it pertains to component 1. So for ethanol, this is going to be the derivative of the mole fraction of ethanol with respect to our position Z. And if we write out our summation, this is going to be the mole fraction of ethanol multiplied by the molar flux of acetaldehyde minus the mole fraction of acetaldehyde multiplied by the molar flux of ethanol divided by our concentration and our diffusion coefficient of ethanol through acetaldehyde. That is going to be added to the mole fraction of ethanol multiplied by the molar flux of hydrogen minus the mole fraction of hydrogen multiplied by the molar flux of ethanol divided by our concentration and our diffusion coefficient of ethanol through hydrogen. Likewise, we can write out one for our acetaldehyde. So this is going to be the derivative of our mole fraction of acetaldehyde with respect to our position Z. And this is equal to the mole fraction of acetaldehyde multiplied by the molar flux of ethanol minus the mole fraction of ethanol multiplied by the molar flux of acetaldehyde divided by our overall concentration and our diffusion coefficient of acetaldehyde through ethanol plus the mole fraction of acetaldehyde multiplied by the molar flux of hydrogen minus the mole fraction of hydrogen multiplied by the molar flux of acetaldehyde divided by our concentration and our diffusion coefficient of acetaldehyde through hydrogen. So just as we did before, we do need to come up with a scaled position to make sure that we're in a range from 0 to 1. So we're going to use that same sort of concept that we did last time with our variable n. So n is our scaled position. And our scaled position is equal to x, sorry, not x. We're working with z, so it's going to be z, the position we're at, divided by that distance from our bulk surface to our catalytic surface. So if we take the derivative of this is going to be the derivative of our scaled position is equal to the derivative of z divided by that distance delta. And if we want to put that back in terms of our ethanol and our acetaldehyde, for our ethanol, our new equation is going to be the derivative of our mole fraction of ethanol with respect to our scaled position is equal to the distance delta multiplied by this entire term here. So we're going to rewrite that out. That's y1 n2 minus y2 n1 divided by our concentration and our diffusion coefficient of ethanol through acetaldehyde plus y1 n3 minus y3 n1 divided by concentration and our diffusion coefficient of ethanol through hydrogen. Same idea is going to apply for our acetaldehyde. That's going to be the derivative of the mole fraction of acetaldehyde with respect now to our scaled position. That is going to be equal to that distance delta multiplied by y2 n1 minus y1 n2 divided by concentration and our diffusion coefficient of acetaldehyde through ethanol plus y2n3 minus y3n2 divided by CD23. All right. Now that we have that, again, we just followed that same concept that we did in part B, using our derivatives and making a relationship between the derivative of the mole fraction with respect to Z and the derivative of our mole fraction with respect to our scaled position. So now that we found that, we can once again do the same idea that we did last time, where we said that this term right here, because we use our scaled position, and we said that that means that we're in a range from 0 to 1, we can approximate this term to be about 1. We can also take a look at our mole fractions and approximate those to be 1 as well, because of their order of magnitude. So if we do that, we can now come up with an equation for our molar flux of ethanol. So we can take these terms here and our term for our distance, and we can set an equation that says that the molar flux of ethanol is equal to our overall concentration and our diffusion coefficient of ethanol through acetaldehyde, and this is going to be divided by that distance delta. Now, if we remember from our previous video, we said that the concentration was equal to the pressure divided by our gas constant R and our temperature T. So if we plug that in, we're going to have that the mole fraction of ethanol is equal to the pressure multiplied by the diffusion coefficient of ethanol through acetaldehyde divided by the gas constant R multiplied by T, our temperature, and that distance delta. Now, we want to find the mole fraction of our ethanol at this catalytic surface, and we're given it at the bulk surface. So we need to find a relationship between the molar flux and the mole fraction at that catalytic surface. And to do that, we're going to have to incorporate our rate constant here, K sub R. So we can say that the mole fraction of our ethanol multiplied by the molar flux of our ethanol is equal to this rate constant K sub R. So if we want to find the mole fraction of ethanol, that is going to be the absolute value of our molar flux of ethanol divided by that rate constant, K sub R. So that's the relationship we're going to use in order to find that mole fraction. Now, if we want to find the mole fraction of the other two, it's a little bit difficult because those are products, and so we can't necessarily relate them back to our rate constant. So to do that, we're going to have to kind of just make a guess for the mole fraction of acetaldehyde at our catalytic surface, and we are going to set our guess to be 0.5. And then, of course, if you want to find the mole fraction of the hydrogen at that, you can simply take 1 minus the mole fraction of our ethanol minus the mole fraction of our acetaldehyde at that catalytic surface. And so now what we're going to do is we're going to take the equations that we just found and we are going to put those in Excel in order to find our mole fraction of our ethanol at that catalytic surface as well as our boundary conditions. And we're going to find the reaction rate per area. and again, the surface mole fraction of ethanol. So that's going to be our main goal when we head over to Excel. Welcome to the Excel portion of this video. To get us started, I put in all of our known values. So our diffusion coefficients, our pressure, temperature, our gas constant, and then I went ahead and calculated our concentration, which we know is the pressure divided by the temperature in the gas constant. I put in our mole fractions up at the bulk surface, as well as our delta, the distance from the bulk surface to the catalytic surface, and our reaction rate. I also went ahead and calculated our values for our molar fluxes using the equation that we had found previously. And one relationship I did forget to mention was that we have, if you realize from our previous portion of this video where I showed the reaction sort of equation, there was 1 mole of ethanol going in. This yielded 1 mole of acetaldehyde and 1 mole of hydrogen gas. And so the relationship is just 1 to 1 to 1. You also would notice in the picture that I drew that we had the flux of ethanol flowing downwards, whereas the flux of acetaldehyde and hydrogen were flowing upwards, which is why I have this negative in here for this molar flux of ethanol, just to show that they're moving in opposite directions. So now we can go ahead and solve for our mole fractions at the catalytic surface, and we said that the mole fraction of ethanol at our catalytic surface we estimated to be equal to the absolute value of our molar flux of the ethanol divided by the reaction rate. So if we take the absolute value of that, this is the number we'll get. And then we said that we were going to estimate the mole fraction of the acetaldehyde to be 0.5. And then the mole fraction of the hydrogen is simply 1 minus the sum of those two values. So we're going to take 1, should be equal to 1 minus this number minus our mole fraction for acetaldehyde. So these are the numbers that we have come up with. Then I'm going to make sure that all of these are formulas so that when we go to insert our equations, it makes it a little bit easier. Once again, just like the previous video, we are going to start our counter at 1,000 and go to 1,000. So to add in those 1,000 iterations, I am going to fill series. We want this going down the column, stepping 1 and stopping at 1,000. We can now go ahead and put in our scaled position. The scaled position is going to be equal to where we're at multiplied by the delta, the distance between the bulk surface and the catalytic surface divided by 1,000 because we have 1,000 different iterations. So if we put that in, we can drag this all the way down. And if we scroll down just to double check at our 1,000th iteration, we should have a value, yes, of 0.001, which is that delta, that distance between the bulk surface and the catalytic surface. So now we can go ahead and put in our different mole fractions at the surface, at the catalytic surface. So again, these were our estimates. So we're going to plug all of those in. Perfect. And we can also put in our derivative of the mole fraction of ethanol with respect to the scaled position, as well as the mole fraction of the acetaldehyde with respect to the scaled position. I do have my iPad off to the side to reference those formulas, but if you need to look back at them, they were in the previous section. So for the derivative of ethanol with respect to our scaled position, that is going to be equal to Y1 multiplied, so the mole fraction of our ethanol multiplied by the molar flux of our acetyl acetaldehyde, and then you'll subtract this from the mole fraction of the acetaldehyde multiplied by the molar flux of the ethanol. This is all going to be divided by our concentration multiplied by the diffusion coefficient of ethanol through acetaldehyde. And then you are going to add that, add that to the mole fraction of ethanol multiplied by the molar flux of our hydrogen. This is going to be subtracted by the mole fraction of our hydrogen multiplied by the molar flux of our ethanol. And this is going to be again divided by the concentration, and this time multiplied by the diffusion coefficient of the ethanol through the hydrogen. So we can put that in, hit enter. The same idea is going to apply for the it'd be the acetaldehyde. So I'm just going to quickly copy this over. We're just going to plug in new values. So we copy this over and paste this. We are going to simply change this from the mole fraction of ethanol to the mole fraction of acetaldehyde, and this time multiplied by the molar flux of ethanol, mole fraction of ethanol, molar flux of acetal anhydride, not acetal anhydride, acetaldehyde, and then still multiplied by the diffusion coefficient of ethanol through acetaldehyde. And then this time, this is going to be mole fraction of acetaldehyde multiplied by the molar flux of hydrogen minus the mole fraction of hydrogen multiplied by the molar flux of acetaldehyde. And this is going to be divided by our concentration and our diffusion coefficient of acetaldehyde through hydrogen. So we put that in. These are the numbers that we should get. Now we're going to use Euler's equation to find our mole fractions as we go through each step. So this is going to be equal to the mole fraction plus where you were, so our scaled position multiplied by our derivative of our ethanol with respect to our scaled position. So we can put that in. We can do the same kind of idea for acetaldehyde. So this is going to be the mole fraction of acetaldehyde multiplied by, plus the scaled position that we were at multiplied by the derivative of acetaldehyde with respect to our scaled position. So we can put that in. And then this, the mole fraction of our hydrogen is simply going to be 1 minus the sum of these two. So this is equal to 1 minus y1, not that. This is equal to 1 minus y1 plus y2. So we can put that in. We can drag these values down. And then we are going to take this all the way down through all of our iterations. So now we can scroll through and make sure that we aren't getting any super crazy numbers here. I don't think that we are. So if we scroll all the way down, we can see what we end up with. So these are the numbers that we end up with right here. And what we want to see, because this is at our bulk surface. So what we want to see is that this is at 0.6, and this is at 0.2, and this is at 0.2. Now, of course, we don't see that. So what we're going to want to do, I'm going to put these values up here. This is going to be G at 1002. This is going to be H at 1002. And this is going to be equal to I at 1002. And yes, so that way we don't have to keep scrolling. So these are going to, this is the bulk, the mole fraction at the bulk surface, which once again, we already have established these values in our problem statement. We wanted them to be 0.6, 0.2, and 0.2. So now let's figure out how far off this is. So if we want to figure out how far off this is, we're going to take our desired value and subtract that from our value that we calculated. And if we take no, so let's find out how far off we are first. So let's do that. And we can do the same idea here. So it's going to be this minus this. And then we can do the same thing here as well. So what I'm actually going to do for all of these is square these. We're going to square this, square this number. And it's a bit redundant, but we can do the same thing for hydrogen. We don't necessarily need it, but we'll do it anyway. And then if we want to find our sum squared value, this is going to be equal to just the sum of those squares. So we'll just take these two, enter in that. And once again, we want to minimize this value, and we want our bulk mole fractions to be as close as they are, or as close as they can be to what we were given. So what we're going to do is use Excel Solver. So kind of the same idea that we did last time. We're going to go to Data and Solver. Once again, our set objective is this sum squared value here. We want to minimize that. And our variable cells are going to be our surface mole fractions, because again, we just took the estimate of those. So that was our initial guess, and now we want Solver to change them to match what we need. So if we put that in there, we want to make unconstrained variables non-negative, so that's perfect. And then we can go ahead and hit solve. Hit OK. So now we can scroll all the way down to the bottom, and it should change it for us. Yes, so now this is perfect, because now at our bulk surface, the mole fraction of the ethanol is pretty close to 0.6, and the mole fraction of the acetyl aldehyde as well as the hydrogen are at 0.2. So that is exactly what we want to see there. So we can see what changed here after using Solver was, of course, our the mole fractions at our catalytic surface. So at that catalytic surface, we can say that the mole fraction of ethanol is about 0.48. The mole fraction of the acetyl aldehyde is about 0.28, and the mole fraction of the hydrogen is about 0.23. So now what we're going to do is we are going to determine the reaction rate per area of our catalyst. So to find that reaction rate per area, we can relate our mole fraction of ethanol to the molar flux of ethanol and then multiply by the reaction rate to get it to be in terms of area. So now what we're going to do is we're going to vary the reaction rate to find the different extremes of different reactions. Okay, so what I did here is that I retook our initial guess for the surface mole fraction and then put that into the equation for the molar flux, and then we have our new sum squared. So now as I scroll through here, you'll see the further we go along, we're getting values of -1 and 1, and this is pretty common in a diffusion limited reaction. So in a diffusion limited reaction, the reactants aren't reacting fast enough, and the catalytic surface is consuming every bit of the reactants. This means that our reaction rate is too high. A couple ways that you could mitigate this so you're not just getting values of -1 and 1, so -1 for the reactants and 1 for the products. You could either decrease your distance, so that delta, or you could actually decrease your reaction rate. So if we want to decrease this to be, let's say, 0.01, we're starting to get some more normal, I'd say, mole fractions. But if we decrease it even more, it'll look more like what we have had. We put this to 0.01. Yeah, our mole fractions are a lot easier to comprehend. Now, if we go ahead and decrease this distance here, let's add in a couple zeros, you'll see that we have even more separation and that the mole fraction of our reactants is super high, which means that our catalytic surface is not reacting enough. Another limited operating condition is a reaction limited operation. And in this case, your catalytic surface might not have the properties to be reacting enough or fast enough, so you might want to reinvest or invest in a new catalyst. Just to reiterate, when I decreased both this distance here and this reaction right here, as you can see, the mole fractions at your catalytic surface are about the same as the mole fractions at your bulk surface. And this means that your catalytic surface is not reacting fast enough. And so that is how we were able to use Excel Solver to solve the Maxwell-Stefan differential equation subject to our boundary conditions and find the reaction rate per area of our catalyst and the surface mole fraction of ethanol, and then vary our different reaction rates and our delta or distances to see what kind of effect that those have on our mole fractions and what that might mean in the real world.